Hello there. In this video, we're going to introduce a theorem and an application from that theorem. So the theorem that we're going to pretty much be exploring is what some people refer to as Leibniz Rule for integration. So Leibniz Rule for integration. And it says this. So let us assume that f of xt and the partial derivative of f with respect to x of xt are continuous in both x and t. Then, if we define some function phi of x to be equal to the integral from a to b of f of xt dt, where a and b are constants, then if we want to find the derivative of phi with respect to x, the derivative of phi with respect to x, of course that's going to be equal to the derivative of the integral from a to b of f of xt dt, then Leibniz rule says we can pass this derivative under this integral sign and say that this is the integral from a to b of the partial derivative with respect to x of f of xt dt. So this is what people refer to as Leibniz rule. So from this rule in this video, we're going to do a couple examples to illustrate it and do an application known as Feynman's method at the end. So let's start working on an example of how to find derivatives of integral defined functions such as this with respect to x. And just a side note here, notice we're looking for the derivative with respect to x of this function. A and b are constants, and this is an integral in terms of t. So let us start off with our example. So let us define f of x to be equal to the integral from 0 to 1 of 3xt plus 5t squared dt. And keep in mind 1 and 0 are t values. So if we pretty much ignore Leibniz rule, let us sort of just figure out what another representation of this integral in terms of x we have. So if this is true, then that means f of x is going to be equal to, so if we're integrating with respect to t, x is going to be treated as a constant. So 3x is the constant coefficient of t, and 5 is the constant coefficient of t squared. So when we integrate with respect to t, this is going to give us 3 halves x t squared plus 5 thirds t cubed. And then we need to evaluate this as t goes to 1 and as t goes to 0. So as t goes to 1, everything is very straightforward. So f of xt is going to be equal to 3 halves x plus 5 thirds times 1. And then when we subtract this evaluated as 0, we just get 0 there. So this is our alternative representation for x. So using some basic standard calculus, we know the derivative of this function is going to be equal to the coefficient of this linear function, which is 3 halves. So that is finding the derivative of this function f of x without using Leibniz rule. So let us see if we can get the same exact answer using Leibniz rule and compare. So example 2. So let's consider the same function. F of x is equal to the integral from 0 to 1 of 3xt plus 5t squared dt. So Leibniz rule begins by taking the derivative of both sides of this equation with respect to x. So the derivative of f of x is going to be equal to the derivative of the integral function 0 to 1, 3xt plus 5t squared dt. So Leibniz Rule says if this function is continuous in both x and t, and as well as its partial derivative with respect to x, which you can verify on your own that it actually does hold, and we have constants 0 and 1 here, then we can pass this derivative under the integral sign and turn it from a total to a partial derivative. So that means f prime of x is equal to the integral from 0 to 1 of the partial derivative with respect to x of 3xt plus 5t squared dt. So if we're taking the partial derivative of this curve with respect to x, we're treating t as a constant here. So that means 3t is the constant coefficient of x, and 5t squared is a constant in its own right. So that means the derivative with respect to x is going to be equal to the integral from 0 to 1, so the partial derivative of 3xt with respect to x is just going to be equal to 3t, and the partial derivative of 5t squared with respect to x is just going to be 0. So this is just going to be 3t dt. So using our fundamental theorem of calculus, we know that this is going to be equal to 3 over 2t squared, and we need to evaluate this as t goes to 1 and as t goes to 0. So as t goes to 1, we just get 3 halves, and as t goes to 0, we just get 0. So we get 3 halves as the derivative of that function, which is indeed the same thing as we had before. So it definitely does work. Now, why would you choose one method over the other? Well, it depends on the difficulty of the integral that you're dealing with. They definitely give you different problems to work with, so it's more of a subjective determination on the calculator's part or the person's part, determine which method do you prefer to use based on the complexity of the function you're dealing with. So an application of Leibniz Rule is an integral calculation method known as Feynman's Method for calculating integrals. So Feynman's Method. So how does Feynman's method go here? So we're going to look at the integral as an example. The integral from 0 to 1 of x to the a minus 1 all over the natural log of x dx. So I'm going to instead rewrite this integral. So this integral is over the domain of x from 0 to 1. So this integral, if it converges and exists, should be a function of a. So our goal is, okay, what is this equal to? So I'm going to define a new function. I'm going to call it, say, f of y. And I'm going to define this function f of y to be equal to the integral from 0 to 1 of x to the y minus 1 over the natural log of x dx. If you aren't sure when to use Feynman's method, you need to sort of figure out, okay, why would I want to use this? So if we take the derivative of x to the y with respect to y, x is treated as a constant. So if I do the derivative with respect to y of x to the y, and I'll just call this a constant with respect to the power y, this is just going to be equal to a to the y times the natural log of a. We're treating x as a constant, so we're just, calling it a to avoid any ambiguity there. So here we have a to the y, or x to the y times the natural log of x, and we also have a natural log of x term in the denominator as well. So we can then cancel out those natural log of x terms, and then we should have a better integrals to sort of deal with. So this is sort of the ideas you would have to sort of think about when you're looking at an integral to determine whether Feynman's method is a good way to go or not. Alright, so if I define this function f of y to be so, then I can take the derivative of this function with respect to y. So f prime of y is going to be equal to the derivative with respect to y of the integral from 0 to 1 of x to the y minus 1 over the natural log of x dx. So this is an x integral. These are limits of x. X to the y minus 1 over the natural log of x definitely will be continuous on the open interval 0 to 1, and you can verify that its partial derivative with respect to x also will satisfy this criteria. So if that is true, we can pass this derivative into here, and it will turn into a partial derivative with respect to y. So we have the derivative of y is going to be equal to the integral from 0 to 1 of the partial derivative with respect to y of x to the y minus 1 over the natural log of x with respect to x. So we're doing a partial derivative with respect to y, so everything that has x in it is treated as a constant. The natural log of x is no exception to that. Derivative of minus 1 is going to go to 0, and we can use the exponential identity for the derivative of a constant to a variable power. So that means we have f prime of y is equal to the integral from 0 to 1 of x to the y times the natural log of x minus 0 all over the natural log of x dx. So as we were talking about before, the natural log of x terms here do cancel, and we're just left with f prime of y is equal to the integral from 0 to 1 of x to the y dx. Now, when we're focusing on this integral with respect to x, y is just a constant in this case, so we can apply the power rule to this expression. So you always have to keep in mind what variable is truly a variable and what variable is treated as a constant in the context of what operation we're doing here. So using the power rule, we can add 1 to that exponent, so it becomes y plus 1, and we divide by that new exponent, and we have a constant of integration there. All right, so what we have here is f prime of y is equal to x to the y plus 1 all over y plus 1 plus c, but we need to evaluate the limits here, so we need to send x to 0, and we need to send x to 1. So the constants of integrations do eliminate here. So x goes to 1, and as x goes to 0. So as x goes to 1, we have 1 to some power, which is 1. So that's going to give us 1 over y plus 1. And 0 to any finite power that's non-zero is also going to be equal to 0. So we just have 1 over y plus 1. So the derivative of f is 1 over y plus 1. So now I'm going to find the antiderivative of f. So if f prime of y is equal to 1 over y, then f of y is going to be the integral of 1 over y plus 1 with respect to y. And that's a very basic integral as well, so we know that f of y is equal to the natural log of y plus 1. You can include the absolute values there if you prefer, plus c. So what exactly have I done here, and what's so special about this function f of y? Remember what we defined f of y to be equal to before. So recall, f of y is equal to the integral from 0 to 1 of x to the y minus 1 over the natural log of x dx. So these two expressions are actually equivalent expressions. They represent the same exact function. And the one that I have shown in green is a general case or the extension of the value for which I am interested in. So these two curves are equal to each other. So the next thing I need to figure out is, okay, what is this value of c? So from this definition, if I plug in the point, say 0, so f of 0 is going to be equal to the integral from 0 to 1 of, so we're plugging in y here, so that's going to be x to the 0 minus 1 over the natural log of x dx, which is going to be the integral from 0 to 1 of 1 minus 1 over the natural log of x dx, which is just the integral from 0 to 1 of 0 dx, which we know is just going to be equal to 0. So this is almost like an initial condition to a basic differential equation. So we say that, okay, if f of y is equivalent to writing the natural log of y plus 1 plus c, and f of 0 is equal to 0, then combining these two expressions, we should be able to figure out what c is. So that means 0 must be equal to the natural log of 0 plus 1 plus c. So the natural log of 1 is going to be 0, so we get c is equal to 0. So if that's the case, then that means f of y, which is the same thing as the integral from 0 to 1 of x to the y minus 1 over the natural log of x dx is precisely equal to the integral, or the natural log, of y plus 1. So now we go back to the equation that we were interested in. Remember that our star integral is the same as f of a, namely the integral from 0 to 1 of x to the a minus 1 over the natural log of x dx. So by this relationship, we see that that's just equal to the natural log of a plus 1. So if that is the case, then we can also come up with another identity, namely the integral from 0 to 1 of x to the a minus 1 over the natural log of x dx is just equal to the natural log of a. And that gives a very nice identity for an integral that would otherwise be not easily obtained. So pretty much how we obtained this integral was via a method called Feynman's method, which is just a direct application of